Good afternoon, everyone. Welcome. So for this session, we are going to talk about distributed algorithms for big data. Let me introduce myself. My name is Yuhai Duan. I'm working as a technical advocate for Apache Cassandra. And by my job, I get interested into distributed algorithms. Today, we are going to talk about HyperLogLog and Paxos. Who has already heard about those two algorithms? Raise your hands. Okay, few of you. Good. HyperLogLog. This algorithm is quite recent. It has been, the first paper has been published by a French guy, Philippe Flageolet, in 2007. So it's very recent in terms of academic research compared to Paxos, for example. The challenge, what is the idea? What is the problem we want to solve with HyperLogLog? We want to count a number of distinct elements. Counting a number of elements is very easy. You have just a counter, you just increment every time. But counting distinct elements is hard. Why? Because we want to do this counting concurrently with a very high cardinality data set. We are not talking about counting 100 items. We are talking about 1 billion, 10 billion items, okay? So there are some solutions, of course. The basic approach is to take a Java hash set, okay? This one. If you have around 67,000 distinct elements, it would require 10 megabytes in memory to count them exactly the number of distinct elements if you are using Java hash set. There is another algorithm I'm not going to present today, linear probabilistic counter. This will give you an estimate of a distinct element with 1% error, and this requires only 3 kilobytes. So this is 3 orders of magnitude lower. And with HyperLogLog, the error margin increased. We have 3%, but this time we only need 512 bytes. I'm talking about bytes, okay? So it is very powerful. We're going to see how it can be achieved. Let's play some rolling dice. We all played this game when we were young, okay? So, first attempt, I roll the dice 100 times. What I can see is this is a distribution of the number I get, okay? And it is not uniform, of course, because it is all about probability. If I do another attempt with 1,000 rounds, 1,000 times I roll the dice, the probability tends to be more and more equal. And of course, if you repeat the same experiment with 1 million times, this time you achieve almost uniform probability. Okay, it is all about statistics. Okay, so why am I talking about dice? Because this is the basics of HyperLogLog. But before talking about HyperLogLog, I'm going to talk about log-log algorithm. Okay. So the idea is very simple. This is the simplified version, okay? You choose a very, very distributive hash function. For every incoming item, an item, it can be an article ID, a login, a new UID from, okay? You apply this hash function to this item. This will give you a number, right? Because a hash is a number. You convert this number into a binary sequence, 0, 1, 0, 0, etc. And the idea of log-log algorithm is by observing these binary sequences, I tried to estimate the cardinality. I try to estimate the number of distinct elements I have. So how does it work? We are talking about uniform probability. How can we have uniform probability? Because we choose a very distributive hash function. This is a very important criteria, okay? So intuitively, we know that half of the bit sequences we will obtain will start with 0 something, okay? Half of them will start with 0, and half of them will start with 1. Fine. Now, if we look at the first 2 digits, first 2 bits, 1/4 of them will start with 0, 0. 1/4 of them will start with 0, 1, 10, and 11. Okay. It is just about simple probability. Now let's define what we call a rank R. A rank R is the position of the first bit set to 1 starting from the beginning of your bit sequence. Okay. For example, here the rank is 9 because the first one starts at position 9. Here the rank is 4. Here the rank is 6. Okay. Simple. In fact, there are 2 power R different combination of bit sequences with the length R, right? 001, 0010, 0011, 1111 of length R. This is just combination, right? So now, let's go back to uniform probability. There will be 1 over 2 power R of the bit sequence starting with 0001, the same amount with the bit sequence starting with 00010, and so on. So before we are talking about half, 50%, and then 1/4, and if you push the reasoning further, if you take into account a bigger number of beginning bits, we get this. Okay. Now we need to reverse the logic because until now it's quite simple. Okay, it's just basic probability. We need to reverse the logic. I have many chances to observe 0001, then to observe 0010, then to observe 0011. I have the same probability, okay? It means that if I have observed 0001 sometime in the past, I should probably have observed 0010 and probably have observed 0011. That's the idea. Uniform probability, right? It means that if I have observed 0001 sometime, there is probably 2 power R bit sequences of rank R. And this 2 power R is our estimated cardinality. Okay. This is how we get from the rolling dice to this number. So the log-log formula was simple. Let's look for the longest position, 001, observed among all binary sequences. Okay, we have all the hash values in binary sequences. We take the longest position, and the estimated cardinality is given by this formula, 2 power max R. It seems very straightforward. But there is a problem with this. Let me show you. For example, I have a set of 1,000 distinct elements, a very small set. Okay, 1,000 is very small. I apply the hash function. It gives me a lot of bit sequences. And sometime because it is purely by chance, I observe this sequence. The rank is 15. So if I apply this formula, it will give me 2 power 15, which is 32,000 and something. This is the estimated cardinality. And of course, it is wrong in my example. Of course, it is wrong. Why is it wrong? Well, because in a statistical theory, you always have what we call outliers element, extreme elements, okay, which give you errors, okay. So this is the idea of HyperLogLog. Because of those extreme elements, we have a wrong estimation. So how can we get rid of those extreme elements? Well, by using harmonic mean, okay, which is a special averaging function. So thanks to Wikipedia, I found this formula. This is the harmonic mean. N is the number of elements. You take the inverse, the sum of the inverse of all elements, okay. And by taking the inverse, you reduce the weight of the extreme element, of course. Let's look at an example. I have 5 numbers, 3, 6, 7, 2, and 1 extreme element, which is 120. If I apply the harmonic mean formula, it will give me 6.80. If I apply the classical average, it gives me 51. Okay. You can see here that harmonic means is very useful to eliminate extreme values. Okay, fine. So, okay, we should apply some averaging function, which is harmonic means. But to be able to apply an average function, you need to have many elements. The second idea of HyperLogLog is, okay, we distribute the computation. How? First, we define P, which is a prefix of the bit sequences. For example, if you select P equals 6, you will have 2 power 6 different combination, okay, which is 64. So this will give you, this prefix will give you the bucket number. We split all the bit sequences into bucket. So you have an input stream of data. You take the prefix, and depending on the value of the prefix, you know in which bucket you will put those bit sequences, okay? Simple. And then we apply the log-log algorithm to the remaining. You take out the prefix, you apply log-log to the remaining sequence, okay? On each bucket, of course. Okay. So you take out, you remove this prefix because it is, this prefix gives you just the bucket number. Then you apply, you try to find the longest rank from the remaining of your bit sequences. So for each bucket I, you can compute the cardinality estimate for this bucket. We call it this MI. So this is the formula of of log-log, okay? We have seen just before. Max RI is the max rank found in bucket MI. In bucket I, sorry. So, a harmonic mean, what is intuitively a mean, an average? An average is equal to the total number, which is the global cardinality estimate we want to find, divided by the number of buckets. Okay. This is the intuition of an average. Average equals to total number divided by buckets. So the global cardinality estimate is equal to bucket number times harmonic means applied to all the buckets. So let's just do a little bit of math. Okay, it is just end of high school maths, not very difficult. So I take the formula from Wikipedia. B is the number of buckets. So 1 over x1. So this is a sum. Okay, so I just rewrite it as a sum, a sigma here. Simple. Taking the inverse of something is equals to this something power minus 1. Okay, simple. And I apply this same transformation here. 1 over xi is xi power minus 1. Simple. So we replace the xi in the previous formula by mi, which is cardinality estimate for each bucket. And this is our formula. Harmonic means is equal to number of bucket times this big formula. Okay. And we inject the 2 power max ri into this formula. We get this. So this is the final formula. Remember, we defined this just before. The intuition of a harmonic mean, we inject HMI into this big formula. There is still one difference. This is this, alpha B. What is this? This is a constant, a corrective constant. Why? Because even if you are using harmonic means to eliminate extreme values, for a very small cardinality, you still have some errors. And in the original research paper, they add this constant to fix the error when you have a very small data set. Okay. What is beautiful with HyperLogLog is the accuracy of this formula does not depend on the number of items. It depends on the number of buckets. So here you have some example. If I have only 256 buckets, I have 6% error. If I have 2,000 buckets, I reduced the error margin to 2%. Okay. It is very intuitive. The more you have buckets, and the less you have hash collision, right? So when can we use, and for which use case is HyperLogLog useful? Well, you want to count the unique visitor on a high traffic website, okay. Number of unique clicks for popular items or article. Cumulative unique visitor. I have applied this HyperLogLog algorithm for a startup. Every day, they use HyperLogLog to estimate the number of unique visitors. For example, they have 1,000 unique visitors on Monday, 1,200 on Tuesday, and so on. So the question is, how many unique visitors do I have from Monday to Friday? You cannot just take the sum, right? Because we want the unique on those 5 days. And what is interesting with HyperLogLog is you can make an union of the buckets. And at the end, you still have the estimate of unique visitor for the union of 5 days, and it works. So this is the beauty of this algorithm. Some real-world implementations. So in Apache Cassandra, we have distributed tables. It means that you have a table. The data are distributed all over the cluster. So imagine you have a cluster of 100 machines, and you want to count the number of distinct elements on your big table. You are not going to do a full cluster scan, of course. So what we did is, on each machine, on each node, we have a cardinality estimate. Let me show you the example. CF stat spark demo albums. So I have a table album. Here. This is the estimate using HyperLogLog. Okay. And if you have 100 machines, on each machine you have a different number. So you can just add up. Okay. In Redis, HyperLogLog is a basic data structure. You can just use it. It is out of the box. For those who are using Apache Epic, there is a standard UDF in Dataflow library. And Twitter Algebra, they propose also HyperLogLog for storm and scaling. Okay. So HyperLogLog is used everywhere. Even if you don't know, it is used everywhere. Any questions so far? Yes.
Which hash functions are used in those projects?
I cannot tell for Redis and those, but in Apache Cassandra, I think it is Mormo3 hash function, which is quite distributive. Yes?
You said the accuracy depends on the number of buckets.
Yes.
But is it the same thing for required space? Required space, the second column of data that I have to see right now.
Yeah.
Is it also depending on the number of buckets, not the number of
No, only in the research paper, this is the exact formula. So it doesn't depend on the required space. The intuition is the more you have buckets, the less you have hash collision, right? Any other question? Fine, it's clear, okay. Let's move on Paxos. Okay, Paxos is a big deal. So Paxos is very old. When you look at the date, 1989. So the first time Leslie Lamport, he wrote this paper, nobody understand. Nobody. Since many years after, he wrote another paper which is Paxos made simple. Because the original paper was not simple. Okay? And even with the Paxos made simple, I read it 5 times before I really understood the algorithm. So what is the challenge? What do we want? Which problem do we want to solve? The challenge is to find a consensus, okay, in a distributed system with the presence of random failure. You can have hardware failure, you can have network failure, whatever. In the literature, we have already two-phase commit, right, for this. The problem with two-phase commit is it is a blocking protocol by nature. And if your manager is down, it requires human intervention to start it up, to restart it. And then, so people devise three-phase commit to fix issue of two-phase commit. But still, there is one scenario when you have a split brain partition, you can have inconsistent state. Okay. So it is not safe. The idea of Paxos is it will cost you 2.5 network round trips. It introduces 3 roles, a proposer, acceptor, and learner. And it needs a quorum of response. What is quorum? Quorum is a strict majority. If you have 5 machines, a strict majority, a quorum of 5 is 3. If you have 4 machines, the strict majority is 3. 2, right? First phase, prepare. Here I have a client. the client asks the proposer, hey, I want to reach consensus on some value val. The proposer will choose a sequence number, what we call, okay. And it will send a prepare and message to 5 or to all acceptors. Here in my example, I have 5 acceptors, okay. After receiving this prepare and message, each acceptor will reply with a promise. Okay, I promise. This is phase 1. Second phase, now the proposer, if he has received a quorum of promise, it means at least 3 promises, it will send accept with n, the sequence number it had chosen at the beginning, and the consensus value the client requested, accept n val. The acceptor will reply by accepted and val. And if the proposer receive a quorum of response, it means at least 3 accepted and val, it will reply to the client, okay, val has been accepted. So this is a very, very simplified explanation, okay? And the last phase, of course, is the learn. Because when you reach consensus on some value, you need to store this value somewhere on disk, okay? Durable storage. So learner are some other machine whose task is to save the consensus value on disk. So now let's go into details of each phase. Phase 1, prepare. The proposer will pick a monotonically increasing sequence number n. So how can you have this number n? Well, you can just take the timestamp, okay, in millisecond. But then you can have collision, because if you have a lot of traffic in the same millisecond, you can have many proposers picking the same value. So one easy solution is to use time UUID, which is an unique ID generated using the timestamp, the MAC address of your network interface, plus a random sequence from the microprocessor. So you are sure that this time UUID is unique and will be always increasing because it is based on the timestamp. So the proposer pick a sequence number n and send prepare n to all acceptors. Fine. Each acceptor, when it receives a prepare n, if it has not accepted any m, or if it has not done any promise with a sequence number bigger than n, then it will return, okay, I promise you, with n, and it will store n locally. Second thing, it will promise not to accept any prepare or accept with a sequence number lower than n. Okay, it is a kind of ordering based on the sequence number. Now, if the acceptor, it has already sent an accepted value with a sequence number, oh, there is a mistake, m bigger than n, sorry, m bigger than n. This time, it will return promise m, the bigger sequence number value, and the proposed value. Okay, it say, oh, sorry, I cannot promise to you because I have already promised to someone with a bigger sequence number, and this is the promised value, which is val m. Okay. Wait. Oh, sorry. This is correct. With m smaller than n, so it returns this. And if m is bigger than n, it will ignore. Okay, because it had already promised to someone else, so ignore. Or it can send a no ACK. So the proposer will not wait until timeout. It is just an optimization. So if it has not accepted with an m bigger than n, it returns promise. If it has accepted with an m slower than n, it returns the already promised value. Otherwise, no ACK. What is the objective of this first phase? It is to discover any pending action to make it progress. Because if the acceptor has already made a promise, it will return this promise. Okay? And it will block all proposals that are stored because of the sequence number always increasing. Second phase, accept. Now the proposer will receive a quorum of promise. Each of them has a sequence number and a value, possibly no value or value. If all of the promise are his sequence number he sent just before, then he will send the accept with his second number and the value he wants to reach consensus. Otherwise, if among all the promises there is already an m with a value, it should send the accept with this existing promise and not his own value. Okay. Again, when the acceptor receives the accept and val, if it has not made any promise with bigger sequence, it returns accept, otherwise it ignores. So it's quite complicated. Okay. And of course, the last phase is the proposer receives a quorum of accepted, it sends a message to a learner. So all this is very confusing with m and n and so on. That's why I read the paper 5 times, okay, before understanding. The objective of the second phase is to commit any pending proposal. The proposer, if one of the acceptors say, hey, there is already a promise ongoing, it should propose this promise and not his own value to make any pending proposal progress. Okay. The problem with this, so this is what we call a Paxos round in the formal paper. The problem with the formal paper is once you reach the consensus value, this value is there forever. You cannot change it. So we need to find a way to reset the value to make another Paxos round. Okay. So in practice, people who implement Paxos, there are many implementations. So one of them is multi-Paxos. The idea is to make many rounds of Paxos in parallel, and each time they reset the consensus value. And each server can be a proposer, an acceptor, or a learner. Okay. So there are many other different implementations based on Paxos. Now, what is interesting to understand this algorithm is to see conflict cases. Here you have a timeline. You go from the left to the right. Okay. Acceptor 1, acceptor 2, acceptor 5. We have 5 acceptors. Each of them receive a prepare n. They return a promise nothing because, well, there is no promise made yet. But just after returning the promise, 2 of them die. Acceptor 1 and acceptor 2, they just die. Okay. Then the proposer will send an accept n a, which is the consensus value. The remaining acceptor will return accepted a, and we reach consensus. Why? Because we have a quorum, we have a majority of response. As long as you have a majority of response, it's fine. You can lose some acceptor, it's not a problem. Second case, now we have a majority of acceptor who die. This is the same scenario, but this time you have 3 acceptor who die. Okay. So this accept and accepted will not reach consensus because the proposer only received 2 answers, 2 responses. And 2 is not the strict majority of 5. And imagine there is another round of Paxos starting. Another proposer will say, hey, prepare N2. This is N1. Prepare N2. Promise. Well, at this phase, those 2 acceptors, since they have already promised to accept value A, they will return this value A and N1 to the new proposer. And the new proposer see that, okay, there is a pending proposal. So I need to propose A again and not my own value. So this second round of Paxos will make this first round progress and will commit it. Of course, after this time, those 3 machines are online again, okay? So this is the fundamental idea of Paxos is if you have some error in the past, the new round of Paxos will commit the accepted value. What happens if we have 2 concurrent proposers? Okay. Last plebiscite wins. You have a first proposer which send N1, prepare, promise, then those 2 machines goes offline. They goes online again. Another proposer will send prepare N2 with a sequence number bigger than N1. And this time those 2 acceptors are offline. When they come back online, they will send accept N1A, N1A, but the problem is the proposer, those 3 acceptors will send a no ACK. Why? Because they have already promised to N2, which is bigger than N1. Okay, so they block this round because N2 is bigger than N1. Okay, and finally, the second round of Paxos will win with B value because N2 is bigger than N1. Okay. And the last case is what happens if what I call inter deadlock. Propose N1, promise N1, propose N2, promise. So you have 2 proposers, okay, trying to propose different values. So the acceptor will accept to first proposer N1. They promise to the second proposer with N2. So when the first proposer push a value, this value will be rejected because N2 is bigger than N1. Okay. So it restarts another round with N3 bigger than N2. And when the second proposer tries to push value B, this will be rejected because N2 is smaller than N3, and so on. So you can come tack. So we have a deadlock here. How can we solve this deadlock? Random slip. Okay. Basic. I am a proposer. I push a value. I get rejected. I slip for, I don't know, 10 milliseconds, 15 milliseconds. So by making the proposer slip randomly, we are sure that eventually, after some attempts, there will be one proposer which will win. Okay. We break the inter deadlock with random slip. There is other strategies to select the proposer. In many implementations, what they did is they select just one unique proposer. So if you have one unique proposer, you don't have concurrency issue, of course. But the problem is now, how can I choose a unique proposer? See? So when do we need Paxos? Well, people need Paxos for reliable master election for master-slave architecture. When you have a master and slave in NoSQL database, well, you need to elect the master in a safe way. You can use Paxos. You can have compare and swap, distributed compare and swap, or distributed logs, okay, based on Paxos. Some implementation, real-world implementation. Well, in Apache Cassandra, what we did is we introduced what we call lightweight transaction, which is a kind of distributed compare and swap based on Paxos. Google, with their Chubby Spanner framework, they use Paxos to create a distributed transaction or distributed logs. Heroku, the cloud provider, they use Paxos via dozer-D to distribute the configuration metadata. And in Neo4j, from version 1.9, they used to have Zookeeper to provide high availability. They replaced Zookeeper with Paxos implementation. Okay. What time do we have? Okay, we still have time. Any questions so far? Clear? Okay. Let's have some demo. So as I said, we implement in Cassandra lightweight transaction on Paxos. So what is the idea? So I will show you how you can implement a distributed log with Cassandra using lightweight transaction. So here I have a table test log, okay, with two columns, the type of my distributed log and then a log ID. So I truncate the table and I insert if not exist. So this keyword if not exist means we are using Paxos behind. If there is already the primary key global, this request will fail. Okay, so it works because I truncate the table before. But if I remove this line, false. See, it says, okay, your request has not been applied because there is already a log ID global. Okay. Now I will list all of my logs. So I have a global log with no ID. There is no log yet. Okay. Now I want to acquire a log, update test log, set ID equals to 1, 2, 3, where types equal if ID is null. So it's a compare and swap, distributed compare and swap. Set the ID value to 1, 2, 3. If there is null means there is no value yet. Okay. I execute. So now I put a log with ID 1, 2, 3. Only me knows that the ID is 1, 2, 3. Now imagine someone else want to text to acquire the log. Okay, so they want to set another ID with the same update request. False. It will be rejected because the ID is no longer null. Okay. So the log cannot be acquired by someone else because he doesn't know the ID value. Now I want to unlock to release the log. So what I do is to set ID back to null if the previous values is equals to my ID number. Okay. So if I do this, then someone else can acquire the log. Okay. So this mechanism is pretty simple, and all of this is based on Paxos. Question? Clear? Yes.
Yeah, I have a question. Where was the Paxos behind those queries? Because I don't see the relation. With
Yeah, we implement every time we see if not exist, if something equals to something in the query, in the statement, we start a Paxos round. So
the numbers in this Paxos round.
the value, the consensus value, well, we choose a random number, but it is like we said, okay, there is a pending Paxos round on this partition key, which is global, okay. Type is the primary key of my table. And any update or insert action on this table, on this primary key, will be delayed until my action finishes. So remember of this diagram. When is this? This. Okay. So I want insert into blah blah if not exist. So I create a Paxos round on this partition key. So there is a compare and swap, because compare is if not exist mean, hey, look on the disk to see if there is no value. If there is some value, it will fail. Otherwise, I will have a Paxos round on this partition key, and if someone else is trying to do something on this partition, it has to wait. Okay, it's like a queuing system. It will take very long time to explain the implementation, because it's I can show you the code, but I don't think it will be interesting for you. But the idea is this. And there is no lock. It means that it's live. So as long as you don't update or insert into the same partition, it doesn't matter. It means that in my example, if I have another type of lock, it can be transaction, blah, 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 it will work. Okay.
Do you know why Neo4j replaced Zookeeper by Paxos?
No. I guess probably that they doesn't want to have another piece of technology in their stack, because Neo4j is already a NoSQL database, and if you want to install Neo4j, you need to install Zookeeper and blah blah. So it's quite complex to manage, you know, on the operational side. So probably they want to remove all the moving parts. But this is just my assumption, okay? I'm not 100% sure. You need to ask them. Any other question? Thank you.